let's summarize what we had from last time. We made one cut, and that was perpendicular to the x-axis. And what we found was then we have one normal and two shear. And now we're going to identify the sign convention that we're going to be using. For either sigma or tau, there are two subscripts, and we're going to identify the following sign convention. The stress is considered positive if it's on the plus face. In fact, let's call those two subscripts I and j. So the first and the second one. So it can either be sigma ij or tau ij. Let's draw that up here. So sigma ij or tau ij. So it is, the stress is considered positive if it's on the plus I face in the plus j direction, or remember we have the same thing that's on the back face. It can either be on, it can also be on the minus I face in the minus j direction. And we can look back to the normal stress to kind of verify that. And the same thing happens with shear. So it's positive, it's considered a positive stress if it's plus plus or minus minus. And that is a state of positive stress. Now this one we already knew. The normal stress we already knew. So for example, sigma xx, that means that if we have an axially loaded bar that looks like this, there is my P, and we slice it like this. Then notice what happens. We get on the left cut, we've got the stresses going this way. So there is the P. That would be the sigma xx. I guess I should put an x-axis there. Then if I looked at the other side, I would have the normal stress going this way. Like so. Same value, sigma xx. So it's both, they're both going to be tensile, even though they're going in opposite directions. Plus face, plus direction, minus face, minus direction. That's a positive stress. And the same thing is going to happen with the shear. All right, they're going to be considered negative, the stresses, if it is on the plus I face in the minus j direction. Or it gets flipped. It's on the minus I face in the plus j direction. So that's going to be our sign convention now, and it's the one that's going to identify and help us to determine what the signs of tau are going to be. And so everything that we've said so far is consistent with what we had for normal stress. So this is consistent. And that was tension is positive, compression is negative. So nothing new about that. But now the sign for the shear, that's going to be new. And it can be a little bit overwhelming when you first see it. So don't worry, we're going to practice this and kind of do some repetitions on it as we work our way through. And it turns out that the sign of the shear is actually going to be a little bit secondary. It's going to come into play a little bit later on in the class. So I'll just maybe give you a little bit of a relief here and say we will practice this, because it does take a little bit of time to let that gel. Now, we made one single cut, but what happens is you make two more. So that after you do this, after the first cut, we make a second cut. I'll double bullet that. And the second cut, that's going to be perpendicular to the y-axis. And guess what happens? You're going to get a sigma on the y face in the y direction. So you get a normal stress. You get a shear stress on the y face in the x direction. And you get a shear stress on the y face in the z direction. So once more, we get one value of the normal stresses, and we get 2 shears. So 2 cuts, 6 total stresses. And then finally, we make the 3rd cut. Perpendicular to the Z axis. And we have sigma ZZ on the Z face in the Z direction. We have a shear stress on the Z face in the X direction. And we have a shear stress on the Z face in the Y direction. So what happens is we've made 3 cuts. Let's put a little therefore or in conclusion. We made 3 cuts through P, and there are 3 mutually perpendicular. In other words, they're all perpendicular to each other. We made 3 cuts, and we have 9 components of stress. But a very cool thing happens. We are not going to show this in this class. If you want to see this, you would have to take the next class beyond this, which is CIVE 560, and that's called Advanced Mechanics of Materials. I know, mechanics of materials, not mechanics of solids. But in that class, what we show is you can use moment equilibrium on a small piece of solid. I'll just write it like this. You can use sum of the moments is equal to 0. And what turns out in a very attractive result is that tau xy, so the shear stress on the x face in the y direction, is equal to the shear stress on the y face in the x. The shear stress on the x in the z is the same as the shear stress on the z face in the x. And finally, shear stress on the y face in the z is the same as shear on the z face in the y direction. So we have those 3 results. So what that means is of the 9, 3 are not independent. So we finally then get to write our conclusion for the general state of stress, and we say, I'll put the double arrow, and we say there are 6 independent components of stress. At any point P. And I do want you to commit that to memory. So there are 6 components that we would get. Now, most of our problems in this class, there will not be that many. We are going to look at fairly simple loading states and fairly simple solids. So we might want to, again, calm ourselves down and say, for us, it is usually less than 6 that are going to be non-zero. In other words, we're going to have a simple loading state. For example, the axially loaded bar with a perpendicular cut, there would be 1 non-zero stress. That would be the normal stress on that cut plane. But that value of 6 is going to be very, very important for us, and we're going to be using that over and over again. And so, if you were to go to Ford or Lockheed Martin or somewhere else, and you're trying to find the state of stress at a point, you are interested in 6 numbers, and they're signed. So if you come up and give one of your colleagues 4 or 7 or 2, that's not going to be quite right. So you're going to have to be thinking about having 6 that you're going to be calculating when you do this particular sort of analysis. All right, now at this stage of our knowledge of mechanics of solids, let's kind of go back to what we originally stated during the outline of this class. When we have a solid and we load it with F or P, whatever we want to call it, but I'm going to go ahead and use F, that's our generic symbol for force, then the solid deforms. It goes into U. So the loaded solid deforms. That deformation leads to a strain, which we have not talked about yet. That strain is linked with a stress, and that stress, when integrated then, gives us a force that balances the applied load. Now, what's this integrating business? What we've talked about here was basically taking the force and divide it by the area. And that's because we looked at the state of uniform state of stress. So the final question that we want to close out before we leave this state of stress is, how do we get from stress to force? So what happens is, if we do have a cut face, and I have something here, and there, let's say we have a non-uniform value of stress. So let's go ahead and say that this would be our X face. And now what happens if sigma XX is not uniform? So in other words, it's not a P over A. How do we get from stress to force? So to distinguish this, let's put a big arrow there and maybe a smaller arrow right there. So we have a normal stress, for example, that is not going to be constant anymore. Well, in this case, we would say that the general way that we're going to get the total force in the X direction, let's call it that. So to get that particular value, so the magnitude that we would want of the total force that we get in the X direction is, we're going to take all the little stresses, all the sigma XX's, multiply it by the area that we have, and integrate that over the area of the entire domain. So that would be this. So we get force by integrating stress. Let's write that down to close us out for today. So we obtain force by integrating stress over the area, period. And of course, if it's uniform, we just get to multiply. So it's easier if it's going to be a uniform. We'll just say if uniform, then we would have F is equal to sigma times A. But in the general state, we want to get the idea that we're going to be integrating over the area. And great work sticking with us, because now we are done with our lecture for today. See you next time.